All right. So first things first, we'll start by going over homework. Let me set that down. So homework, we started with the algebra review at the end of chapter 2, right? And then let's just go through it real quickly. Under what? No, that's wrong. Prove that if x equals 7, then 4x plus 5 equals 33. How did we do that?
You say, observe that x, 4x.
Yeah, you just plug it in.
What problem are we talking about?
Number 1 on the algebra review.
Oh, well, we did.
So proving it the first way was really easy, right?
Yeah.
Proving if x equals 7, then what was it?
Then
4x
plus 5 equals 33.
And then all you did was plug in. Observe that 4 times 7 plus 5 is equal to 33. 33 is equal to 33. So that way was easy. Now, problem 2 says to prove the converse. And here's where we actually have to use our algebra theorems, right? Now, I'm a little annoyed that the author doesn't specify exactly what he's doing. And since these algebra reviews come up again and again at the end of each chapter, here's what I'm going to assume that we know. I'm going to assume that we know what it means to plus. I'm going to assume that we know what it means to times. And then that we know that those are associative and commutative.
Right.
Does anyone here not understand what we mean by addition is associative or addition is commutative? Laura, what's associative?
I don't know.
All right. So associative means that if we have a plus b plus c, parentheses there, that's equal to a plus b plus c. We can associate any two together that we want, and it doesn't change it. Commutative is order doesn't matter. A plus b is equal to b plus a. So I'm going to assume that we know that addition is associative and commutative, and the same thing with multiplication. So in other words, a times b times c is equal to a times b times c. That's associative. And then commutative, a times b is equal to b times a. So I'm going to assume that these are the properties that we know when we're talking about these things to begin with. And then as we go through, he's going to add some definitions, he's going to add some theorems, and we'll continue. So he gave us 2 theorems to use in this one. The first theorem he gave us, not theorem, sorry, axiom. The first axiom he gave us was if a is equal, maybe he did it this way. No, he did. If a is equal to b, wait, a plus c is equal to b plus c implies a is equal to b.
Yes. No.
And yes.
Yes.
And then he also gave us that if a is equal to b and c is not equal to 0, that implies, oh, I did that backwards.
If a times b equals.
If AC is equal to BC with C not equal to 0, then that implies A is equal to B. Right? So this is all the information that we have to call upon to do these proofs. So this first proof, all we had to know how to do was know how to times and know how to add. Right? So the second one's a little bit harder. So if 4x plus 5 is equal to 33, so that implies x is equal to 7, right? How did we do this? Well, we started with 4x plus 5 is equal to 33, right?
Yep.
Then we use one of those. What are we going to use?
One.
Yeah, we're going to use axiom 1. So then 4x is equal to 28. That's my axiom 1. Now what's my next line?
That 4x is equal to 4 times 7.
Perfect. 4x is equal to 28.
Then you're going to use
X
it
equals
to.
Use the second one. X is equal to 7 using the second one.
Right.
Right?
Yep.
Perfect. And then the rest of the problems were very similar to that.
Yes.
I don't think any of them got interesting again until, was it number 12?
There was some like number 8.
Number 12, 12 had to start.
We were not supposed to do the one start.
Oh, really?
Yeah.
You guys are so lazy.
No, we're supposed to learn
Oh.
first.
Oh,
I'll show you the
number
next
8 was a
one.
weird one.
If
Prove
and only
that there. Which one do you want to do?
if. The if and only if.
What number?
7.
7. Prove that 2x plus 7 equals 19 if and only if 4x minus 3 equals 21. Okay? So when we do if and only if statements, remember what if and only if means. If we have A, if and only if B, that's like this, right?
Yeah,
And there's a couple ways that we can interpret that. The common way to interpret that is A implies B and B implies A, right?
Yeah.
Now, before we continue, I actually want to talk about something because that I've seen in your homework. If I'm writing a sentence and the word equals comes up in the sentence, so if I'm writing an essay and I say that equals blah, 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 and I continue like that, do we ever use equals like that in the middle of a sentence?
No.
No. This is equivalence relation. You might not know what that means, but it talks about two different things. We use words here. So don't use and like this. When you're writing along and you need to use the word and, don't use that symbol. That's like using plus for the word plus when you're talking about it in an essay. It's very strange. This is an operation that takes two numbers. This is an operation that takes two booleans. Don't use it for and. If you want a short way of writing and, just use the ampersand sign or write out the word and. But that is very uncommon to use the word and that way. And similarly with or. Now, when I write proofs, I'm going to use implies as arrows a lot. That's commonly done in proofs. This implies this. We use arrows a lot to do that, so that's fine. But don't use and or that way. No one's going to know what you're saying. If you're just writing along, you put this little hat thing and you continue writing. All right. So continue. So if we want to show A if and only if B, we need to show A implies B and B implies A. If A, then B, and then we need to show if B, then A. So read me what the problem says.
Oh. Prove that 2x plus 7 equals 19 if and only if 4x minus 3 equals 21.
Right?
Yep.
So when you're doing if and only if statements, or if and only if proofs, another convention is when you're proving one way, you start that out with an arrow pointing like that. We draw the arrow path. So I'm going to prove that A implies B, and then somewhere later in my proof, I'm going to say, now I'm proving the other side. B implies A. So that's just convention to break up your proof into logical blocks so people know what to expect and what follows. Okay? So we're going to start with proving this one. So we're going to assume this is true and prove that means that this is true. Okay? All right. So let 2x plus 7 equal 19. Right? Well, what does that mean? That means 2x plus 7 equals 19. That means that 2x is equal to 12. That means that 2x is equal to 12. That means that x is equal to 6. Right?
Yeah.
Now that we have x, we can kind of just use that to reconstruct this right-hand side of the statement. You see what I mean? Okay. So then if x equals 6, I'll rewrite that here. That implies 4x. Ooh. Maybe I'll just skip to this. So I'll forget what I said before. So now we'll say, so we have x equals 6. So then 4x minus 3. Oh, here's what we'll do.
Equals.
So 4x minus 3 equals what? That equals 4 6's minus 3. That equals 24 minus 3 equals 21. And so that equals that. So if this is true, then this and this and this and this and this and this and this, then this equals this equals this equals this. You follow the logic there?
Yeah.
Yeah.
All right. So now we'll do it the other way. Let 4x minus 3 equal 21. Right? That gives us 4x minus 3 equals 21.
No.
Daddy, why do you
18
have
minus
to do it
3.
backwards if you already proved that it does equal 21? So by already putting 6 into that equation,
You're proving
because it
A.
equals
B implies A. That's what we're doing.
So she's got a pretty good question. So you're basically saying we just barely proved this, why are we proving it again, right?
Yeah.
And this is, it's true that we could just reverse these steps basically and get back where we started, and it works that way with equations. That happens to be true. It's not something, like it feels so obvious to you that that's true because that's what you've been doing so much. But for example, if I were proving that S less than 6 implied something, I'm trying to come up with a good way on the fly to make this appeal to your intuition. Here's one way we can say it. We showed that if this is true, then x has to equal 6. And if x equals 6, then this is true, right? But we don't know that x is the only solution to that. You might know that from previous math, but how do I know that there's not some other number that I can plug in there and get a different answer?
I see.
Right? Now you know that there's only one solution to that, and that happens to be true. But if that were switched out with a quadratic, then this would be, you'd have to use different lines of reasoning.
Then couldn't you just solve for 2x plus 7 equals 19, and then solve for 4x minus 3 equals 21, and then say that they're equal to each other?
Say that they're equal to each other.
So you find that if x equals 6 for the first equation and x equals 6 for the second equation, then you can say the equalness is.
So then all we know is that if x equals 6, then these two things are true. That doesn't tell us if this is true, then this is true. We need to show that if this is true, then this is true, and then we need to show that if this is true, then this is true. Okay? It's weird to do it with equations to begin with because you want to assume knowledge that you already have. So it's hard to do accurate proofs to begin with because you're proving things that seem so obvious. And we'll see even more of that when we get to the next chapter, the algebra review, when we start proving properties about negative numbers. So, yeah, let's continue. So let's see. If 4x minus 3 equals 21, then 4x minus 3 equals 21.
4x equals 24, and 4x
Maybe I'll write it
equals
one more
4
way.
times
4x plus negative 3 equals 24. Now, I also don't like that he's already introducing negative numbers because at the end of the next chapter, he's going to define negative numbers for us. So,
He's introducing them before he's defining them.
yeah, which is kind of bad.
Yeah.
So we're going to kind of cheat and pretend that we have knowledge about negative numbers for now, and then come to the end of the next chapter, we're going to forget that.
Okay.
I don't know why it does it that way, but we'll continue. So that's true. Then
4x equals 24, and then
4x equals
6
24, which gives 4x equals 24, which gives x equals 6.
Now,
So then, which one were we doing?
we're
We're showing this implies this, right?
Yes, so we plug this.
So then 2x plus 7 is equal to 2x plus 7 is equal to 19, right?
Yeah.
And so there's our if and only if proof. Now, obviously I skipped a bunch of words I didn't mention when I was referencing theorems, but You should just be checking your homework, and so you should just validate you did it right. Right?
Sure.
Sure. You cheated?
Probably.
Well, that's not good. All right. So should we skip to 12 now? Did anyone do 12?
Oh, you told us not to.
I didn't tell you not to. I said you don't have to.
Dude,
I didn't say thou shalt not do 12.
I actually need your help with that. Is it the, oh wait, never mind. It's a 12 on a different one.
Yeah, we're talking about 12 on the algebra review.
Yeah.
We did 12 in class.
Yeah, we did. But I'll warn you of this probably 10 times as we go throughout this class, and I'll warn you again right now. You're going to see me do proofs in class. Your brain, as you're seeing me do it in class, is going to say, I understand, I understand, I understand, I understand. Then if you go home and try to reproduce that proof, you're going to get stuck. That is going to happen several times. I promise you that you will have that experience unless you're just already good at geometry. So even after I prove something in class, it is great to see if you can reproduce that proof. Now all the proofs that we're going to be doing early on are kind of trivial proofs, and so maybe you can just see what's happening. Once you know the trick, and you can continue. But as proofs get more complex, for those of you that took my discrete math, you can probably vouch that I can do a proof for the class 3 times and then put it on the test and they'll all miss it. Huh, man? All right. So let's get to 12. I think that's the most interesting of these and probably captures the rest of the ideas that he was trying to capture in this. Oh, shoot. Didn't mean to erase those.
You can still see it.
You can still see it?
Yeah.
Try and re-scribble in real quick what this said. A plus B plus C is equal to that. We're going to pretend that we knew what plus and times were. This was A times B times C, A plus B, A,
1,
A, and this was number 1,
2,
number 2, A, C.
Yeah.
All right. Cool. Someone want to read me number 12 so I don't have to keep holding my book?
Oh my god. Okay, it is known that 2a minus 3 times b minus 3 equals 2a minus 2. Prove that if a equals 1, then b equals 3.
If, say it one time.
If a equals 1, then b equals 3. And then there's a different proof.
Also,
Yeah, so we'll start with this one. So prove that if A is 1, then B has to equal 3, right?
Yeah.
So let's start with that one. So if A equals 1, B, so let A equal 1, right? 2. Then 2 times A minus 3 times B minus 3 is equal to 2A minus 2, right? Which gives us 2 minus 3 times B minus 3 is equal to 0. And then we'll just call that -1 for now. -1 times B minus 3 is equal to 0. Now what?
Okay, -1 times 0 is
we
0.
made so that the 0.
-1 times 0 is 0, right? So we can rewrite 0 this way. We can rewrite 0, right? And then B minus 3 equals 0, or in other words, B
equals 3.
plus -3. You can't just get straight to B equals 3. Equals 0, right?
Yeah.
And then B equals 3. You have to use these things.
Bro.
You can't pretend
I
you
don't
know what you already
understand.
know.
I don't understand why you gotta say 3 plus -3.
What is this number?
0, but still.
So I didn't change the value.
Oh, you just rewrote it.
I rewrote 0.
Change the value of the left side. And what
No, I
you do to
didn't.
the left side, you have to do.
Right here to here. You're saying going from here to here?
Never mind, I got it.
You got it?
Yeah.
Good.
Get it?
Okay, so that was if A equals 1, B equals 3. Now the next one is if B is not equal to 3, A is not equal to 1, right?
No,
If
it's
A is not equal, then B is not equal.
Say that again. You can't talk.
Other way around.
If
A is not equal to 1, then B is not equal to 3.
Okay, so that one's weird. How do we use that information?
We think about it in terms of B proving and going to A. I don't know. B implies A.
Positive.
Use the contrapositive. So we know that, does it make sense that every time we're proving a theorem, we're showing A implies B?
Yeah.
Is everyone comfortable with that idea?
Yeah.
So we can use logically equivalent versions of this thing to do our proof. And A implies B has the exact same truth values as not B implies not A. This is called the contrapositive of that, right?
Yeah.
Right.
These are logically equivalent. If you do the truth table for this and you do the truth table for this, you get the same thing,
Right.
right?
Yes.
Is there anyone who needs to see that? It'll take 10 seconds to do, so let's just do it if we need to. We're good? Okay, so we're going to use the contrapositive on this. So what's the contrapositive of this?
B equals
1.
3.
Oh.
If B equals 3, then A equals 1.
Perfect. So this statement right here is logically equivalent. That statement is logically equivalent to not B implies not is like not B implies not B.
Yeah.
Not B implies not A. Sorry, I'm using B and A ambiguously there because they're also our variables. Not this statement implies not this statement. Right?
Yep.
What's the contradiction of B equals 3?
That B doesn't equal 3.
That B doesn't equal 3. So that is a contradiction of that. Right? And same thing the other way. Okay. So these two things are logically equivalent. So if we prove this, we've proved this. Right?
Yes.
So let's prove this. That's a lot easier to handle than proving this. I don't even know how to think about that. That's weird. But this, we know how to wrap our hands around. And then it's almost identical to what we just did, right?
Yeah.
So we start with 1, let B equal 3. Then 2A minus 3 times B minus 3 is equal to 2A minus 2. Right?
Yeah.
Which gives us 2A minus 3 times 0 is equal to 2A minus 2, which gives us 0 is equal to 2A minus 2, right?
Yeah.
Which gives us 0 is equal to 2A minus 2. Then we're going to use
Number 1.
number 1 to rewrite that. So get rid of both those minus 2's. So 2 is equal to 2A. So,
Using number 2.
not yet.
Then, yes. Oh, it has to, you have to times it by.
What do I rewrite right here?
2 times 1 times 2.
2 times 1 or 1 times 2 is equal to 2 times A. Now we can use number 2 and we get 1 is equal to A. Good? Or, well, yeah, A equals 1, same thing. Okay. Do any more of the algebra review ones look interesting to any of you, or should we continue?
No, they're on
I
board.
couldn't figure out how to do number 11.
Number 11, let's do it. Number 11. Well, rather than me pulling this book, does someone just want to read to me?
It is given that 3a plus 12 times 2b minus 8 is equal to 0.
2b minus 8.
Yeah. Is equal to 0, and b is not equal to 4. What can be proved?
What can be proved? So we know this. If b does not equal 4, what do we know?
So what'd you do by contradiction?
If b is not equal to 4.
Yeah, what's a good way to wrap the logic around this? Do we all see big picture how we would go about doing this?
No.
Do we?
We try
In
to
other words, I'm saying right off the top of our heads, we know that if b is not equal to 4, a is equal to negative 4, right?
No.
Oh, you don't even see that?
What the what?
Oh, yeah, yeah, I see it, yeah.
What?
Because if you had it b equal to 4, then you would get a...
Yeah, I'm trying to think about the rule that we could
you
use
get
for
a
this.
positive on this side, and then you get a negative on that side.
If b equals 4.
You'd have to find what b is
put it
equal
If
to.
it's
A
not
equals
equal
0.
If b equals 4, then you have 8 minus 8, which is 0. And then if a equals negative 4, you have negative 12 plus 12, which is 0.
Oh, I didn't see that.
So maybe we'll break this up into 2 steps. Here's kind of how I'm seeing it. Let's show that if b is not equal to 4, then this is not equal to 0, right? And then we know that the only way that this number can be 0, this product can be 0 is if the first term is 0, because a number by itself isn't 0, and so the only way to get this side to 0 is to make this one 0, and then we can work with that to prove what we know about a. Does everyone understand big picture what I'm saying?
You're trying to get the right side to be 0 so that b doesn't have to be 4.
I'm trying to show this thing can't be 0, this whole thing is 0, therefore this thing is 0.
Right. Okay.
That's big picture what I'm saying. Everyone good with that? All right, so I'm going to show that b is not equal to 4 implies 2b minus 8 is not equal to 0.
Yeah.
How am I going to show this implies this?
By showing what it would be if it was.
The contrapositive. I'm going to prove that this implies this. Right?
Yes. Right.
So,
You're going to say
1, using
Oh, you're saying what can be proved.
contrapositive, let 2b minus 8 equals 0. Right? Then 2b minus 8 equals 0. Oh, yeah, right. So then, using number 1, 2b is equal to 8. Or in other words, 2b is equal to 8. And then using number 2, so going from here to here we use number 1. And then going from here to here we're going to use number 2 to say that b is equal to 4. Good? So, we show that if b is not equal to 4, 2b minus 8 is not equal to 0. Good?
Yep.
So then I'm saying 3, let c equal 2b minus 8, comma, and observe c is not equal to 0. Just using a dummy variable to talk about it. So 4, then if 3a plus 12 times c is equal to 0, 3a plus 12
Must be 0.
is equal to 0. Good with that?
Yeah.
Looking at you, Yellow. All right. So then it's exactly how we would think, right?
Well, wouldn't that imply that C is 1?
No.
Why?
So
Any number.
we
times
have
0.
something times something that's not 0 equals 0. Right? The only way that I can, if I know that C is not 0, the only way that something times C can equal 0 is if this something is equal to 0. For example, I could put in 56 here and it doesn't change anything. If this times 56 equals 0, this has to be 0. Good question. Everyone understand that? So C is just some non-zero number. So we know that C is not 0. And so this term has to be 0. Good? All right. So then we have 3a plus 12 equals 0. Or in other words, 3a plus 12 is equal to 0. Or in other words, 3a is equal to negative 12. Or in other words, 3a is equal to negative 12. Or in other words, a is equal to negative 4. And then we do our little bobs. Good?
Oh, never mind.
Guys, that was interesting. I wonder if they intended us to prove that or just state that. Because I thought the reason that the other one was start is because we had to use a contrapositive.
So you could use
And we
any
ended up having to use
number,
other
you could use any number in B except 4,
Yeah, plug in any number that's not 4.
but have the other side equal 0, that means.
No. Plug in
The
any
only
number
way
that's
that-
not 4.
Wow.
If this whole thing equals 0, then A has to be negative 4.
That's what I'm saying.
Okay. Good?
Yeah.
All right. Any other interesting ones from the algebra review?
Nar.
Nar?
No.
No? Is that what nar means?
Yeah.
All right. Nar.
What about 9?
What about 9? It's like Mim was wrong. What can you infer if it is known that A is not equal to 0 and that A times 3b minus 8 equals A?
Then 3b minus 8 must equal 1.
Perfect. So we can use this one directly on that one, right? So
Yeah.
doesn't matter. If I have x times A equals A, where A is not equal to 0. In this case, they plug something in for x. But it doesn't matter what expression you plug in for x right there. I can do 3b minus 75, doesn't matter. If I have x times A equals A, where A is not 0, then I can use this theorem directly. Maybe rewrite this as A times x equals A times 1, x equals 1. So in that particular case, they had for x 3b minus something, minus A.
So 3b minus 8 equals 1.
Yeah, so we know that 3b minus 8 in that case equals 1. Or, in short, b equals 3 if you carry out the whole proof after that. Right? Cool. Good. Like when you have questions, means you actually did the homework. Or you're currently thinking about the homework, which is the next best option, I guess. All right, any other algebra review? You thinking about it?
No.
Nar?
Nar.
Nar. All right. So let's move forward. I don't remember why I sent you guys this homework.
Neither do I.
3, 1, and 3, 2 exercise group.
We just did 3, 1, and 3, 2.
Yeah.
How many of you did that? 3, 1, and 3, 2.
Partially.
I did 3 1. I did something.
I did 3/4.
What do you mean you did some of it?
I didn't finish everything.
All right. So number 1, restate the point line and the 3-point postulates, in other words. So let's just go through that. James, what's the first postulate?
First postulate is, are you wanting me to restate it?
Yeah, just tell me what it is. I'm a 2-year-old, and you're telling me what that postulate means. Tell me.
You're saying, okay, so the first postulate is saying is when you have 2 points, then there is exactly one line going through.
No, that's not the first
That's
postulate. That's the second one.
Well,
Oh, is that?
you said
That's two.
Okay, I got mixed up because it says restate, point line.
Yeah, I don't care what the question says.
Okay.
All right, we're just going to go through it. So he gave us number 2. If you have 2 points, there's only one line that goes through those 2 points. There's not 2 lines that go through those 2 points. There's only one. That was the second postulate. I think. Maybe it was the
It
third.
was
Is it the second?
yeah. There are at least 3 points which do not rely on one line.
All right, Laura, what's the
One
first
line.
postulate?
First one is in a plane, then there are at least 3 points, and they don't all lie on the same plane.
Perfect. We'll pick on Leah for the last one.
There are 2 points in every line.
There are 2 points in every line. Perfect. So 1, there's at least 3 points in a plane. 3, there's at least 2 points in a line. 2, if you have 2 points, there's only one line that goes through it. Right?
Yeah.
Right.
All right. What?
I have a quick question.
Okay.
Oh, was it on the other algebra? Shoot.
Oh, you're still looking at algebra review?
No, I thought it was in this one, so I was waiting for this one to come up. In the algebra, I'm wondering what's the difference, again, with if, then, or sorry, only if, and if and only if.
Okay. So
B
let's go through that
implies-
one more time. And we'll write out all 3 of them and write out what they mean. So if I have a sentence and the verbiage of the sentence is, oh, that was terrible. Purple's been doing well for us. Use purple. So if the verbiage of the sentence is A if B, so some statement if that statement, then the logical notation for that is B implies A. Okay?
Okay.
I'll go to the zoo if I have zoo tickets. That means if I have zoo tickets, then I'll go to the zoo. A only if B is A implies B.
Okay.
No.
Really?
See, that.
Yes.
No, that's
I
if
thought
A
it was the other
then
way
B.
around.
No. A only if B.
Bro, what?
I will only
It's
go
not
to
what
the
we
zoo
agreed
if
on.
I have zoo.
Huh?
That's not what we agreed on.
I thought only if B implies A.
Yeah.
I thought that same thing. That's why I asked.
No. A only if B is A implies B.
Oh. Okay.
How? Because it's saying only if B.
Then A.
You can't do A.
All right.
Only if B.
Let's set it up.
A exists only if B happens.
Get our markers ready.
Aww.
Which one should we make A? We'll make A purple, B green. And we need to do a truth table, I guess. A, B, A, only if B. And then to see it all in unison, we'll do A implies B right here, right? We got true, true, false, false, true, false, true, false. And let's fill these out. Oh, we know what this one is, right? True, false,
False.
true,
True.
true. I'm going to throw a marker at you.
Hey, I'm singing and.
All right. Now it's this one. Set up the case. I'm holding a purple marker only if I'm holding a green one.
True.
Okay, that didn't help.
I'm holding a purple marker only if I'm holding a green one.
False.
Should be true. No, he said only if, which means it has to be false.
He's holding a purple one.
I'm holding a purple marker only if I'm holding a green
I
one.
see it now. I see it
False.
Okay.
I'm seeing it.
I'm holding a purple marker only if I'm holding a green one.
True. Because they're not.
It's not false, so it's true. Right? And then true again. We don't need to go through that. There you go.
Okay.
No, that's good. You're going to get stuck on that again and again and again.
So
So-
you're telling me.
I'm telling you that this truth table is valid.
All right.
Will you do the truth table for the if then? And compare it?
Sure. Let's tack it on over here. So, let's do A if B, right? And then we'll also do B implies A. So let's fill out B implies A real quick.
True.
True. False.
False.
Perfect.
True.
All right. So now let's set it up. Setting up this case, I'm holding a purple marker if I'm holding a green one.
True.
True. I'm holding a purple marker if I'm holding a green one.
True.
It's not false. You can't
No, it's
prove me
true.
wrong.
Yeah.
So if it's not false, then it's true. I'm holding a purple marker if I'm holding a green one.
False.
False.
Wait, is B green?
And then finally,
Yes.
true. Yeah, B was green, blue was purple.
Okay.
So I set the scenarios right. So if the scenarios made sense, and they should make sense. So A if B, B implies A. A only if B, A implies B. So A if B is B implies A. A only if B is A implies B. So if we have A if and only if B, then that means we have this and this. This and this is the same as logically equivalent. Right? We already did the truth table for A implies B and, maybe put parentheses, and B implies A. That gave the same thing as A if and only if B.
Yeah.
Right? And that's why we say if and only if when we're talking about that thing. Because of that right there. Good? Alright, great question. Apparently we need that review. Try not to erase all my stuff again. Leave that there. Alright, any other questions or do we continue while I'm erasing this? Start seeing if there's anything.
Okay.
You're all golden?
No, you can do 12 if you'd like.
I already did 12.
No,
For the
on the exercise group.
Okay. hold
Oh,
on.
so now that's what I'm saying. Should we go to the exercise group?
Oh, I thought we were there already.
No.
Oh, you did 9, didn't you, James?
Well, he's just asking about logic in general.
What do you mean I did 9?
You told
Don't
me.
worry about what she's saying. Do you have any more questions? Yeah.
He raises his hand. So I got, for some reason, really confused on 3. Now it's just saying that they have to be the same line if we go through the same points.
Are you looking at the?
Stick.
You're looking at exercise group now?
Yeah.
Yeah.
All right. Yeah. So now we're going through the exercise group. So let's continue through the exercise group. So we did number 1. Number 2. Prove that if L is any line, then there is at least one point not on L. How do we prove that?
You use postulate 1 and 3.
Postulate 1 gives you that directly.
Yeah.
You don't need to use anything else,
Well,
right?
3 just states that a line is drawn between the 2 points.
Oh, okay, yeah. So we've got a line. Number 3, we got postulate 3 gives us that there's at least 2 points on the line. Postulate 1 gives us that there's at least 1 point that's not collinear to those 2 points.
Wait, why don't you need to use postulate number 2 as well?
Because we already outlined.
For any 2 different points.
Okay.
All right, now number 3. Let's go over number 3 real quick. So number 3 says, explain why both
A and B.
Oh, so let's not bother with that. Let's just do the proof.
Where's the proof?
There isn't. It's Theorem 3.
So Theorem 3.1. So this follows from Theorem 3.1. So let's just prove Theorem 3.1 real quick. Theorem 3.1 says to prove that, well, Theorem 3.1 says that if you have two lines, they intersect in at most one point, right? So what's the contradiction of intersecting in at most one point?
That it is not
Intersecting at two?
No, that
Anything.
that it doesn't intersect at
More than one, or at least two, because we don't have the concept of half a point or whatever, right? So, assume, well, maybe we'll start with let L and M be two lines, right? 1, 2. Assume
that they intersect.
by way of contradiction that they intersect
At more.
in at least 2 points. Call them A and B. The picture to help guide us in our proof. Remember, if your proof's valid, you shouldn't be relying on the picture. The picture is to help your intuition. It's not what you rely on to prove. It might help clarify to your reader what you're talking about, but your proof should stand on its own two legs, independent of the image. But the picture that we use to help us think about this is, so we've got two lines. We have no concept of lines being straight right now, so we don't bother with that. And they intersect at 2 points, right? A, B, this is line L, and this is line M. We're showing that this is impossible. That's what we're showing. So assume by way of contradiction that they intersect at least 2 points, A and B. Now what?
You pull out the
Postulate.
pull on 1, 2.
What does that tell us?
For 2 different points, there's exactly 1 line.
Yeah, if you have 2 points, there's only one line going through.
That's
So-
stupid.
Using 1, 2, well, 1-2, using 1, 2, L equals M, right? They're the same line. That contradicts them being 2 different lines. Good?
Yeah.
That's one way that you can say that. So that's all that problem was referencing again, right? So explain why both L and M in this figure intersecting at A and B is impossible.
Yeah.
Because they're the same one.
Yeah, because it forces A and L to be the same, or M and L to be the same one.
Or M or L doesn't exist.
Yeah.
What?
L or M.
Well, no, if I'm given that L and M intersect at A and B, then L and M are the same line.
Or one of them doesn't exist.
All right, if they lied to me,
They did, obviously.
well, no, those 2 lines intersect at the same point. They're just not 2 different lines. They're the same line.
Okay, but
So if we
we're-
assume that they're 2 different lines, but L and M be 2 distinct lines, maybe I should have written
it
there.
says in figure 3-8, that means we're looking at these lines, and one of them cannot exist.
Okay, sure. Okay, number 4. Prove that if L is a line and P is on L, then there is another point on L.
Well, you
Postulate.
just
You
use
just use
postulate 1,
postulate.
3.
Yeah, that one's real easy. We already know that there's 2 lines on L just using a postulate to begin with. So them giving us 1 point didn't help us in any way. Right?
Yep.
All right. Next. Why can we not prove that there are more than 3 lines in our plane?
Because we can only
We
say
cannot
that there's
prove
3
there are more
dots,
than 3 points.
Right, we only are guaranteed the existence of 3 points so far.
which can make
Right?
3 lines.
And when you have 3 points, and you're using 2 of them to create combinations, there's only 3 combinations you can make, right?
Yeah.
For those of you that took discrete math, there's only 3 subsets we can make of the set containing 3 elements.
Yeah.
two-element subsets, I mean. Same thinking there. Now I completely lost my place.
We're on
6.
6.
What page?
47.
Oh, I was on the right page. No, I was one page ahead. Okay. 47.
State.
What does it mean for two lines to intersect?
Means they share.
Sure.
One common point.
They have a common point. That's what it means. Suppose that L is a line. List all the things you can say about this line and points of the plane. We'll skip that. Given figure 3.9, what can you conclude about L and M? They're the same line. We won't bother with that. That's the same as this,
Or
basically.
only one line exists.
Or one of those lines is not really a line and they lied to us.
Yeah.
A line L contains the points P and Q. The line M also contains P and Q. What can you conclude?
That they're the same
That
line.
they're the same line,
Or one
where
does
they're
not
lying to us
exist.
again.
Yeah. It's on all of them.
Two lines have a point A in common. What can you say about the lines?
That they either intersect or they're the same line.
So either they lied to us again or they intersect. The answer is they intersect, by the way. In case I'm confusing anyone by indulging Miriam here. The correct answer is they intersect.
Bro.
Not that they're the same line.
Yes. Why can't L and M be the same line?
Because then they're not two lines.
They're
one
both
line.
lines. That's my point.
So if there's two lines and they have a point in common A, then they only share one, they're intersecting. They're not the same line.
Donnie,
They
they're two
could be.
different letters. They have to be different lines.
All right.
Yeah.
Prove that there are at least two lines on each point. That's finally an interesting one again. Okay, let's prove that there are at least two lines on each point. So let's begin that one.
Okay, there are at least.
You use all 5 stuff.
Yeah.
1, 3, 4, you go 1.
Not to use
So prove there are at least
two lines.
two lines through any point. All right, how are we going to prove that? Where do we begin?
Number
Well, first you
number
gotta
1.
say when you have 3 points
Points on a plane.
on a line, then there are
We
3
don't say
Postulate 1.
for any of the 3 points. Okay. This is an important piece of logic to get your head around to begin with. When we're proving something is always true for any case, we need to start with an arbitrary case. We need to start, let A be some arbitrary point on the plane. Pick any point on the plane and give it to me, and I'll show that two lines intersect that point.
Let A, B, and C be points on a plane.
No, let A be any point on the plane.
Oh.
You don't get to start with 3 points.
Why?
This-
There are at least 3 points on a plane.
There are at least 3 points on a plane. So let's say that we know for sure that this point, and this point are on the plane. Right? And then we prove that at each of those points 2 lines intersect. Did we show that at any point on the plane 2 lines intersect? No, we showed it for those 3 points.
That's what I did.
That is bad. So you need to start with, let A be any point on the plane. We're going to pick some arbitrary point on the plane. And it's a piece of logic that's hard to get your head around to begin with, but you discrete math people, I've annoyed you so much about this, hopefully, that you're starting to get your head to think that way. You need to start out with some arbitrary case. Let A be any point on the plane. Okay, now we can begin. So now we've got any point on the plane. Now we need to show 2 lines go through that thing. How are we going to show 2 lines go through that thing?
You have 2 other points.
Now we know that there are 2 other points. 2. Then there's. How many of you are comfortable with that?
There exists.
How many of you are not comfortable with that? Okay.
Tell us what it means. What is
It means there exists.
Okay, that's fine.
You good with that?
Yeah.
I may accidentally write it all over the place, so may as well just
You
force you to
figure
get
it
used to
out
it.
as it goes.
There exists. Then there exists points B, C on the plane. And that's postulate 1, 1, right? Now what?
Then you say draw a line.
You can say.
Draw a line?
A line.
We have no concept of drawing in our geometry.
You can say.
Then BC.
Say draw lines because there's 2 points.
What are the 2 lines?
A, B, and AC.
Sure.
Then there exists lines A, B, and AC. I don't know. We need to specify containing A. Maybe I'll just write it. Containing A. How do we know that?
By postulate.
Postulate 1, 3. Postulate 1, 3 says if you have 2 distinct points on a plane, then there's a unique line containing those 2 points, right? Okay. And last thing, how do I know that that and that aren't secretly the same line?
Because of.
How do I know that it's not? Here's AB, and here's AC, and that really just gave me this line.
Because that leads
They're non-collinear
Because in postulate 1, A, B, and C have to be non-collinear points. Postulate 1 says there are at least 3 points on the plane that aren't collinear. So I probably should have said, then there exist points B, C on the plane such that, you know what that? Such that?
Yeah.
Such that A, B, C are non-collinear. Right? And then that was using postulate 1, 1. Okay. So maybe we'll specify that for observe that AB is not the same line as AC because
A, B, and C are not collinear.
A, B, and C are non-collinear. So there we go. So we got 2 lines that aren't the same line going through A for any point on the plane. Good? Okay, that one was fun. Why, when looking at this figure, can we not prove that there are at least 5 points in the plane? Are you guys looking at that figure?
Yeah.
There's no way for us to guarantee basically that line DE and BC aren't the same line. This is before we have our betweenness axiom, so we can't say D is between B and A, and therefore it's a different point than B. So right now, D and B could be the same point, and there's no way for us to tell the difference.
So what I said was that we only know that there are 3 points on the plane. Or that there are 3 points. That only 3 of those points exist.
There is a, we only know that there is a.
Meaning D and B could be the same point.
3 points on.
We know that there's only at least 3 points, and we know that there's only at least 3 lines. There's no way that we could disprove that DE and BC are really the same line and the same points in that picture. Good? Alright. Moving on to the betweenness ones. You remember your betweenness axioms?
Yes.
What's the first one?
The first one, I don't know. I know the second and the third.
So the first betweenness axiom, we'll just recap them real quick. The first betweenness axiom says that if B is between A and C, and that's how we write it, if A, B, C, if B is between A and C, then A, B, and C are 3 distinct points on a line. So if B is between A and C, then these points are collinear, and they're 3 distinct points. That's what the first one gives us. Good?
Yeah.
The second one gives us, so this is what the first one gave us. The second one gives us that if we have 3 points on a line, one of them is between the other 2.
Yeah.
Good? The third one, I can't remember if this is the third or the fourth, but one of them is the line builder postulate. That tells us that if we have 2 points on a line, call them A, B.
That's fourth.
Then we're guaranteed that there's a point in between them.
And
And we're guaranteed that there's a point after B such that A, B, D, maybe. So C is between A and B, and we're guaranteed that D is such that B is between A and D.
Yeah.
Good?
Yeah.
And then this is the third or the fourth. This one says that if we have 4 points on a line, any 4 points on a line, it's possible to label them A1, A2, A3, and A4 such that the only between us relations are A1, A2, A3, A1, A2, A4, A1, A3, A4, and A2, A3, A4. Right?
Yeah.
So these are the only between us relations for those 4 points.
Yeah.
And then the fifth postulate
Oh, the between.
in that group says that when you have a line in the plane, so here's some line L,
That it divides.
then all the points are split up into 3 sets.
2 sets.
3 sets.
Oh, because the line.
There's the points on one side of the line, A, over here. There's the points on the line, and then there's the points on the other side of the line, B. Right?
Yeah.
And if A and B are on the same side of the line, what does that mean?
They're in the same
They're
set.
on the same side.
They're in the same side, they're in the same set, but what does that mean? What information does that give us about A and B with respect to
They're
L?
on the same side. as
That they're
line
not
L.
on L. They can't be on. There can't be any points on L.
Perfect.
I know
There
what
is
you're
no
trying to say.
point between A and B on
Yes,
L.
On L.
Right?
Yeah.
And if A and B are on opposite sides of the
It
line,
has to be.
well, I don't know why I wrote that upside down, because I was tipping my head, I guess. B. I did it with the A too, sorry. I write for me, not for you. So, and then if they're on opposite sides of the line,
Then there has to be one on L.
perfect. Then we're guaranteed that there is some point, C, such that C is between A and B. And C is on the line L. Right?
Yeah.
Wonderful. So that's a quick recap of the 5 postulates that we know from our between us axioms. So far we have 8 postulates, right?
Yes.
And by the way,
We have.
it's going to pay off to just memorize them.
Yeah.
They're real easy to memorize them. You use them so much. If you're having to look up every time you're proving, you're not going to get far. It's good to just know what tools you instantly have at your disposal to start proving things. All right. So that's a recap of the between us axioms. Now let's use them real quick. Let's see. Draw a line and mark 5 points on it. Say what the between us relations are. You can do that. Are any of those interesting? For 3-2, exercise group 3-2. Which of those do we like? Were there any that you had questions with? Maybe that's a better way to phrase it. Any that you had questions with, any that you can prove, any that you just got stumped on, any that you thought about, any that you read? Let's start with which ones you read.
6.
You read 6?
Yeah.
That's good. Let's see which ones I did. I usually do the ones that I think are interesting.
Yeah.
We already did number 5.
Exercise group 3-2. We did number 5. Do you remember how to do number 5?
Yeah.
All right. Who said yeah?
Oh, no.
Mim did? All right. Mim's going to approve number 5 for
No,
us.
no, I'm not. No.
Do you know how to do it?
You have to figure out how to assign the lines. You can't just assume.
Who knows how to do number 5?
I used to.
No one?
Let me check my notes.
Oh, so this is one that we should review because you don't know how to do it?
Yes.
Oh, so at the beginning when I said, are there any that you didn't know how to do? This was one that you were like, I don't know how to do number 5, pick me. I'm so desperate to get the answer because I spent so long trying to do it. Right? Okay, let's look at number 5. 5. If A, B, C, and D are 4 points on a line, and we know that A is between C and D, and that C is between A and D, what are the other betweenness relations? Oh, this one was easy.
Yeah.
Oh, I remember this.
Okay, so let's look at what we're given. So, draw this. So we've got A, B, C, and D are points on there. I don't know which one's labeled which, so I'm just going to draw 4 points on there. And we know that A is between C and D, so A has to be one of these two. So far, this one might be A, this one might be A. And then C and D has to be one of those two, and C and D has to be one of those two. Maybe I'll just write to the side what we know. Now I lost it. CAD. And what else do we know? CAB?
Yeah.
All right, perfect. So we know CAD and we know CAB. So that guarantees us that C has to be right here.
And it's either B or
A has to be right here. But we could write BD or we could write DB. Both those satisfy what we were given. Neither of those two scenarios contradict any information here. Right? So what are all the betweenness relations? State a wall for this case, state a wall for this case.
Oh my gosh.
Oh my gosh.
Why did you say prove it?
Did it say prove? I don't think
You
it said
told
prove.
me, okay, it's gonna prove this one.
Well, I didn't know what the problem said.
I was like, no,
I just
cannot
assumed
do
that if you guys want to go over one, it's a proof. Because those are the hard ones. Alright. So let's move on, I guess. Any other interesting ones on there? Like maybe number 12?
Yeah.
12, sure.
Still sorry.
Yes, well,
Yeah.
So that was one we did last time, right? So I'll just look at mine instead of trying to read out of the book. So let's see, 12 says that we were 12 given. It gave us a lot of weird information, but it's logically equivalent to this. Given A, B, C, and D on
A line.
line L. Oh, just on a line. Given those on a line
Prove.
such that ABC and BCD prove ACD. Right?
Yeah.
Okay, so let's try and get a picture in our head of this. So we've got 4 points on a line, A, B, C, D. Let's see what we know. We know that B is between C and D, and that C is between A and D. So we know it goes B, A, C, D, right?
No.
Did I do that wrong?
ABC.
Yeah, it's ABC.
It's the alphabet.
B is between
A and C.
B is between A and C, thank you. So we have, oh yeah, A, B, C, and then B, C, D, perfect. And then prove A, C, D. So that's how we need to do this, right? So, 1, let A, B, C, and D as given. Up there, right? Now what are we going to use?
The postulate. 2, 3.
It's either 2, 3, or 2, 4.
And it's both.
we're going to use a postulate that says if there's 4 points on a line, then it's possible to label them A1, A2, A3, A4 such that we're only between us relations or the 4 relations it gives us, right?
Yeah, that one's 3.
That's two.
No, it's 3.
2, 3. All right, so we're using 2, 3.
5 is the between one.
It's literally 3.
Let me see.
Okay.
We don't even have a.
So let's note that.
Remember them.
Yeah, sure.
Observe that it
Yeah, there's
is possible. Oh, do you know how to book, Larry?
No.
very
Are
good.
these for use?
These are for use. Now, they're also expensive and irreplaceable because it's a textbook from 1960.
Okay.
So I want you to bring it to class every day with you so I can validate that you still have the book, haven't lost it. And then go steal Proverbs from him and bring it back if he's not going to come to class. So I want it back. All right. So observe that it is possible to label the points A1, A2, A1 comma, A2 comma, A3 comma, A4 such that the only betweenness,
Two
two
ends.
S's?
2 ends.
Betweenness,
Between ness. Another S.
I know. Betweenness
That's how it was.
relations are A1, A2, A3, A1, A2, A4, A1, A3, A4, and A2, A3, A4. Okay? So we know that there is some way of labeling these A1, A2, A3, A4 such that these are the only betweenness relations, but we don't know how to label them. We can't just say, let C be A1, D be A2, A be A4, and that be A3. We need to figure out which of these points correspond to which of those points.
This is the one I thought we were doing before.
Now, we know 2 relations. We know that B is between A and C, and B is between C and D.
C is between B and D.
Oh, B is between A and C, and C is between B and D. And we're also guaranteed that these are the only 4 possible betweenness relations. So we know there's 2 of them. We know that these are the only possible 4. That means that 2 of these 4 are secretly those.
Yeah.
So we need to figure out which of these correspond to these 2. Now we notice this starts in 2 points different. This starts and ends in 2 points different than this starts and ends in. So we need 2 relations that start and end in different points than the other one. Now we'll notice that the only ones that have that property are
The
this
fourth
one
And the first.
and the first one.
Yep.
So either this corresponds to that or this corresponds to that.
Or that corresponds to that.
Yeah.
What I said is true.
Yes.
So, observe that A, B, C is A1, A2, A3, or A, B, C is A2, A3, A4. Right? So let's handle the case that we know it's not. Show it's impossible for this to be true, so this one has to be true. Right? So for if A, B, C is equal to A1, A2, A3, then what's D?
I thought we were showing it.
Oh, oops, I meant to use this one. Thank you. If that's A2, A3, A4. Alright, so if it's equal to that, then what's D?
A1.
Then D equals A1, and use one of our things that has D in it. BCD is equal to, what would BCD be?
A2, A3, or A3, A4, A1.
A1. And there's our contradiction, right? That is not one of these betweenness relations. It's impossible for this. Five. Therefore, A, B, C equals A1, A2, A3, and D equals A4. Therefore, let's see, what's the relation we're looking for?
A1, A3.
A1, A3, A4.
Yeah.
Perfect. Therefore, A1, A3, A4 equals A, C, D. And we're done. Good?
Yep.
No questions? All right.
Beautiful.
All right, let's do 15. Did anyone prove 15? That I didn't help?
I think I did it.
You think you did it? All right, come up and do it. Let's see what you get.
Oh.
Because I want to see if you do it different than I did it.
I didn't even know there was a
I
15.
don't know that I'm assuming anything is going to be.
Right. Let me write out the problem real quick and make sure everyone understands the problem, and then we'll continue. So, 15 says, a line does not contain any of the vertices of a triangle. The line L does intersect side AB, but does not intersect side BC. Prove that the line L intersects AC. So, let's get a picture of what we're talking about real quick. So we're given that there's some triangle ABC. I think the author puts the A at the top.
No, a C at the top, B where you put it, and an A on the other side.
So he does A here.
B.
B.
A.
A and C.
C.
All right. So we've got that, and then L's coming through this way.
Yeah.
So here's L.
We know that it intersects BA. We're proving that
So-
it intersects CA.
Whoa. Given L intersects BA, and does not intersect CB, and, I should have said that better, and does not contain any of the vertices, right? Prove L intersects CA. And I probably should have said this better when I wrote it. It intersects segment BA, not line BA. We're not talking about the line that goes through BA. We're talking about the segment.
Just draw a thing over it.
Why is that?
A segment over BA.
Oh, no, because I'll introduce that notation later for something different.
Oh.
Just to tell you right now, when I do AB and I put a line there,
It's line.
I mean the length of.
Oh.
Means repeating.
Oh.
A, B, A, B, A, B, A, B.
Yeah.
All right. So everyone understands the problem? And maybe we should point out why this proof isn't trivial for a second. So here's what you know out the door. You know that this goes through here, and so that there's some point here that it intersects at.
Not the other side.
How do we prove that it intersects this thing down here?
I must have, it's the opposite.
The growing line.
Oh, or vice versa. See, you might be tempted to think the growing line postulate, right? I have a point here, I'm guaranteed that I can pick some other point over here, right? And I can, I'm guaranteed that there's a point here, and that there's a point here, and that there's a point here. I'm never guaranteed that I can get past that line. I could put an infinite number of points and never get past that line.
Yeah.
So I could keep building this line forever, adding infinitely many points to it, and never get to the other side of that line. And never even get to the point where it intersects. So this proof isn't as trivial as you might think. So think about it for a second. See if something occurs to you. Before you see his proof of it. Because the proof's always cooler when you try to figure it out and then you finally see it. So you all understand the problem? Raise your hand if you were able to prove this. Just Mark? Alright, Mark, come show off.
So, Theorem 2, 6, postulate, state is the opposite side.
Postulate 2.5.
5.
If you're using the lines.
I guess we don't
what's
even
the
need
point?
the postulate. We just need the definition of same side, right?
I don't know. Let's see what you do.
So the definition of same side, opposite side is that a point does not lie, a point on L does not lie between B and A. So we know that B and A are on opposite sides of L because L segment AB, right?
Yeah.
It intersects AB at a point not A or B.
Right.
Everyone good? Okay.
And we know that B and C are on the same side
How?
Because
it does not intersect CB.
So show that. Show that if it intersects CB, then we get a contradiction. Or no.
I'm assuming intersect.
What you're saying technically works, but you need clarification here. Let's see. You're saying BC are on the same side of this line. How do you know that? Show to me that if BC are on different sides of that, then we get contradiction.
Why can't A and C be on the same side?
So you can say B and C are on the same side because if they're on opposite
See,
sides, they
this is the assumption I didn't know.
Right, so let's fix it right now. How do we know that B and C are on the same side? This is a trick to the proof, is justifying the statement.
Because line L is on a shut
Hold on.
Hey,
So
how do you
it's
know
like
that?
Because it's
It's
given,
still
because there's no point to L, which is
Oh.
given.
Given how it intersects.
yeah, it's
So you're making an assumption that the only way for B and C
to be on the same
To-
side.
Is that the
Because L is
definition?
in between them.
Or is that-
So we know that there is no point on L between B and C.
Yeah.
So they are on the
Yeah.
same
By
side.
the
Which
given.
says that it's on the same.
Which is the
Or on the
definition of
same
same side.
Same side.
Postulate 5.
Yeah.
2-5.
Okay, so it kind of works, but let me get you guys have the thinking, right? So now let me just give you the right verbiage. Line L divides the plane,
Into two
right,
sides.
into three sets.
I
Those on one side, those on the other side, those on the line.
Yeah.
So C has to be in one of those three sets.
Yes.
C can't be on the line because
It
the
doesn't-
line doesn't contain any of the vertices. C can't be on the side opposite from A. Or sorry, C can't be on the side opposite from B, because if C and B are on opposite sides, then there's a point on L between B and C,
Yeah.
Yeah.
right?
Okay.
And the segment BC contains all the points between them, so then there would be a point between them on the line, which means the line intersects the segment, which we know that can't happen.
Yeah.
And therefore, the only possible case is the third case. C is on the same side as B. So you need to go through those three cases and tell why can't be this case, can't be this case, so it has to be this case. Good?
Yeah.
Okay.
It's kind of a stretch to say, I know that there's only two sides of a line, And so these have to be on the same side because otherwise there's an intersection. There's an explanation that needs to go in there. Do you see that?
Yeah.
Okay. So now we've got B and C are on the same side.
Okay.
Right?
Same side of them.
Are on the same of L.
There, yeah. There you go.
Okay, so since B and C are on the same side, then we know that A and C are on opposite sides. And then using that same reasoning, we know that L intersects segment AC.
Well, we don't need to use the same reasoning for that one. Once you know they're on opposite sides, the definition of A and C are on opposite sides is there exists a point on L between them, right? So you can actually just make that leap. Now, there's one more thing that he's saying here. He went from B and C are on the same side to A and C are on opposite sides. Now, I think that this was a theorem that we already proved.
Yeah.
So if B and C are both on the opposite side from A, then B and C are on the same side. Oh, I said that backwards.
Yeah.
If B and C are on the same side, then B is on the opposite side of A and C is on the opposite side of A. I think that that was another exercise, another theorem that was proved.
Yeah.
But that's something that takes proof. We don't get to just assume that. Just because B is on the opposite side of A and C is on the opposite side of A, then B and C are on the same side. Can't just assume that. Got to prove it. And it's a small proof. You do handle the cases, prove that some lead to contradiction. Therefore, the only case that's left is the true one. Kind of like we proved C. There were 3 cases. C was either on the line on one side or on the other. And it had to be on this side. Similar thinking. Good? So that was a cool problem. And he did it the same way I did, looks like, basically. So that's too bad. I don't know if there's another way to prove it. It's just always interesting to see 2 proofs of the same thing. Let's see. Exercises 3-2 is what we were looking at. Any more of those look interesting? Maybe look at 18.
Yeah, 18 is pretty interesting.
Well, I have one from a previous chapter that we could prove.
Let's look at 18 real quick. 18 says, given a line, prove that there's a point, there's at least one point on each side of the line, right? Now, given a line, we know that there's at least a third point. So using postulate 1, we get the third point, right? Now, how do we get a point over here?
By using the definition of opposite sides on the same side.
Well, we know that if there's a point over here, it's on the opposite side of that, but how do we know that there's even one over there?
different set.
How do we know that this set's not empty?
Oh.
There's one line that
Well,
can
can you say there's a line?
There's one line that contains that, sure.
and then
And
you
then
build the line.
Then you build the line.
Then you use the line builder postulate. If you have 2 points on the line and there exists a third line past this point,
Third point. Pass.
there exists a third point past it such that that one's between those 2 points.
Right.
And notice now, since this one's on the line, we can go that one little infinitesimal place past the line to get past it, right?
Yep. Boom.
So we couldn't use that one for the other one, because if we have a line going here, we know it goes here, and maybe we know those 2 points. We can never add a point on this side and be guaranteed it gets passed over here.
Yeah.
But over here, since we're already at the line, adding another point past it gets us to the other side of the line. You understand the difference between these 2 cases?
Yeah.
One of those, it worked. One of those, it didn't. Perfect. All right. So now the test I promised you. You ready?
What's a triangle?
You forgot about the test?
I don't even know.
All right, we'll do the test next week, and it'll just be based off of your homework that I'm giving you today, okay? Good? And you're all going to be ready for that test?
Sure.
Yes.
And I'm going to post your scores up here.
Yeah.
You.
I won't even put them on the board because I might erase them. I will go through the effort of actually printing them out and hanging them up here. No one's going to bother ripping those down. And for you girls that don't know, they do pre-C meeting in here. Some people meet in here, so people will see them. A lot of boys will be looking at your scores. So they're going to know how bad you did. And a lot of 12-year-old boys are going to be looking at your score, Lawrence. They're going to be laughing at you.
I don't care.
All right. Let's see, let's see. So I think we've covered all homework. Are we ready to jump into new material now?
Sure.
Right?
Yeah.
How far did we get?
We had like 6 pages.
You got through the angle stuff, didn't you?
And the rays and all that, yeah.
Oh, yeah.
So let's just look at my notes now from here on out. So we talked about the definition of a ray.
Yes.
We talked about the definition of an angle.
Yes.
We talked about vertical angles,
Yeah.
adjacent angles,
Yeah.
Oh.
supplementary adjacent angles.
Yes.
That's the
Straight angle.
two adjacent angles whose opposite sides make a straight angle. So I have two adjacent angles, like that. And then the opposite side, so the non-adjacent ray. So here's the adjacent ray. The two non-adjacent rays create a straight angle. So then this angle and this angle
Are supplementary.
are supplementary adjacent angles, is the verbiage that the author uses.
Connie, how would you prove that an angle is a straight angle without measurements?
We already did it.
If both the rays that compose the angle coincide with the line. So one way I might prove it, for example, is if this is a point A and this is a point B, then this point O is between them. And if O is between A and B, then those are all collinear. It depends on the context. I don't know what I'm given, right? So maybe they tell me, you know that this point on this ray and this point on this ray are collinear. Prove that they make a straight angle. Something like that. How do you prove that they make a straight angle? You prove that that's a line. I don't know. I'm coming up with stuff off the top of my head, but do they give a problem like that that you're thinking of?
No, I was just wondering.
Okay.
Because that's how we always proved it was straight angles, through measurement instead of line.
Yeah, that's a bad way to do it because it's only 180 degrees in what we call parabolic geometry or Euclidean geometry. In other geometries, it could be more than 180. In other geometries, it could be less than 180. So that's a bad way to do it, in my opinion, because it's only true for one case. And you should try to be as general as you can.
Will you cover?
Oh, I'm supposed to be looking at my notes.
Interiors and
Not
exteriors.
Yeah, I'm pretty sure we're on interior next year.
Oh yeah, and then we got theorem 3-4 was. Oh, it's not 3-4. That's fun. It's 36. That's fun. So let's try and hurry up and get to that.
Oh, we're not there yet?
We are.
So definition of the interior or the inside of a triangle.
What
Did
page?
we already talk about the interior of an
Yeah.
angle? Is
No.
that where we left off? So interior of an angle.
Right.
Okay, so we're on 3/6 the section. That's where I'm going to start. Interior and exterior of an angle. Okay? So what's an angle?
The angle is 2 rays.
Two rays from a common vertex, right?
Yes.
So we've got some vertices, O, and we draw two rays out from that. So we've got this one, and then I can just draw one like that again, right? And we got a straight angle?
No.
No? Because that's the same ray, that's not two rays,
Yeah.
right? Okay, so we can draw two rays out from that point. And now we've got an angle. Good?
Yeah.
Okay. And we're defining the interior of this. Both these rays can be extended into lines, right?
Yeah.
So So if this is ray 1 and this is ray 2, maybe we'll call this full line L1 and L2. So now we look at all the points on the same side of L2 as R1, right? That's all these points.
Of L2 is R1.
All the points on the same side of L2 as R1. So R1's on this side of L2. Take all the points on the same side of L2 as R1. You understand
Yes.
the language I'm using? All right? And then we take all the points on the same side of L1 as R2. The intersection of those two sets is the interior. So if all these points up here are the points A and all these points up here are the points B, then A intersect B. You guys aren't good with that, are you?
Not yet.
Yeah.
I won't use symbols and I'll just talk. All the points that are on this side and on this side and not on R1 and R2 are the interior. You good?
Yes.
All the points that aren't on R1 and R2 and that aren't on the interior are on the exterior.
Right.
So everything on R1 and R2 isn't interior and isn't exterior. All the hash ones, the lines going this way and this way, are the interior. Everything else is the exterior. Question, is the origin the interior or the exterior?
It's neither.
Neither, because it's on the rays. It's on the angle. Good. So that's the definition of the interior of an angle.
So any of the points on the rays are not interior or exterior?
Correct.
Those are right angles.
So this is the only interior where both lines are?
So let's go over Theorem 3-4 real quick. So 3-4 says, so this is Theorem 3-4. This says if P and Q are interior to O, then so is the segment PQ. So if points P and Q are in the interior of angle O. You go with that? Angle O?
Yeah.
Then the segment PQ is in the interior. Right? And let's get a picture of that real quick. So we've got some angle O. So there's some point O. Here's the angle. We've got P, some random point on the interior. We've got Q, some random point on the interior. We're saying if P and Q are interior points to angle O, then the segment PQ is completely interior to O. Good?
Yeah.
All right. So let's begin. 1. Let angle O, P, and Q exist as stated above. Right there. Okay? Just being lazy to save time. Now, how do we prove that this whole segment is interior? So what is a line segment? A line segment is the point P, the point Q, and all the points in between. So if I want to prove that all the points in between are also interior, how do I do that? I say I grab some arbitrary point out of there, and I prove it's on the interior. Good? So my line here is going to be something along the lines of, let A be any point such that what?
Pack.
Such that pack A is between P and Q. That's how I'm going to begin this. I need to prove it for any point in between those. And if I prove that any point that you grab in between these is also in the interior, then we've proved it.
But since you're only proving it for one point, wouldn't you actually have to try to prove that A is not between P and Q?
No. So let's think of an intuitive example. Has anyone got one off the top of their head? What we're saying is, look, you can grab any arbitrary point off of there. All we're going to use is the fact that we know that that's between P and Q and prove that that's enough information to determine that it has to be on the interior. So we're not taking any special point. We're not taking the one that's right in the middle. We're not taking the one that's right there. We're not taking the one that's right there. We're saying any point that satisfies the criteria that's between those two things, I'm going to show how you can guarantee that it must be in the interior.
Okay.
Right?
Yep.
Maybe here's an example off the top of my head that is similar to it. It's our proof that there's no largest number. So assume, by way of contradiction, x is the biggest number.
2G's.
X plus 1, sorry, 2G's. X plus 1 is greater than x.
Other friends.
Well, that's,
Oh.
you just proved it the way I was saying that should you prove it. You assumed it by, you proved it by way of contradiction, right?
Oh, well we could, shoot.
It seems like in the geometry class I took, we were told just because you proved it for one example does not mean you proved it for
He's
every.
saying-
Right, so we're not taking an example of a point, we're taking
Any
any point, an arbitrary point.
Okay. That makes
Yeah,
sense.
okay. Sorry, I can't come up with a good example off the top of my head. Alright, so let's continue. Let A be any point such that A is between P and Q. That's all we know about A because every single point here satisfies that property. Okay? So every point satisfies this. So we can plug any point in for A and this works. Alright.
on the line, on the segment, on the line segment.
Oh, and I may continue this.
Oh, I guess that it means.
Oh. So I'm going to reference these lines. Let's see. I'll call this R1 and this R2, and then this line L2 and this line L1. You okay with that?
Yeah.
And I'll just reference them from there and I won't bother stating them. So, then we're going to prove, how do I show that A is the interior of this angle?
You show that it's in the set.
Right, I need to show it's on the same side of L2 as P
And Q.
and Q, but just one of them is enough. And then I need to show that it's on the same side of L2
L1.
as P or Q. Doesn't matter which. And then that's enough to say it's in the interior, right? That's the definition of the interior. If it's on this side of L2 and this side of L1, then it's in the interior of the angle, or it's actually on those rays. No, it can't be on the side and on the rays, so that's enough to state it. Okay? So,
Show that it's on the same side.
assume, by way of contradiction, that A and P are on opposite sides of L1. I guess doesn't really matter which one we start with here.
That means it wouldn't be the A.
Just take care of both of them at the same time.
Well, yeah, we can. What we use one way, we can use the other way, right? Observe that if A were not the same side of L1 as P, as P and Q, I guess I stay here. Observe that if it were not the same side of L1 as P and Q, then there would have to exist points P double prime, or P prime and Q prime on L1. Such that P prime A
So
Sorry, I lost track of my own thinking. Let me just write what I'm saying here and then read it. So let's see. Observe that if A were not on the same side of L1 as P and Q, comma, then there would exist P prime and Q prime on L1, oh, that's what I'm saying, such that, yeah, recaught my train of thinking writing it out. So here's what my picture's saying. So my picture's saying, let's pretend that A is over here, right?
Well, it could be like a squiggly line.
L1 over there somehow. So we've got P, Q, and somehow A is over there. Let's not write these so collinear, so that might be like, here's P, here's A, here's Q. Try and make it a little bit more believable.
Okay.
So then there would exist P prime and Q prime on L1, such that P prime A and A Q prime Q. So in other words, then there has to be P prime and Q prime like that.
Can you explain prime?
It's just, it's another variable name. It's like using subscripts. So maybe, it's just what the author does, so I'm trying to get you comfortable with that. Typically I do P1 and Q1. But P prime and Q prime, it's just another variable name without introducing a bunch of other variables. I could have called that S and T or whatever, but notice it goes A, P prime P, and A, Q prime Q. It's just so you can see the similarities.
Okay, wait
What
a
is
second.
the postulate that says that? I know it.
Okay, so if A is on the opposite side of P and Q, by definition of it being on the opposite side of the
That's a
line,
point.
then there has to be a point on the line such that that point is between the two.
Okay.
So if I have a line here and I know that A and B are on opposite sides of the line, the definition of that is that there's some point on the line in between them. So if P and A are on opposite sides of the line, then there has to be some point, call it P prime, in between them. And if Q and A are on opposite sides of the line, then there has to be some point Q prime between them.
Okay.
Are you up to date with me?
Yeah.
Sorry, I lost track of my thinking there for a second because when I write it on paper, I write a lot instead of breaking it up. So everyone get up to this point? Now what?
I don't know what you're trying to do.
We're trying to prove that this is impossible. So we're trying to show that if A were on this side of the line, then we get an impossible picture. What's impossible about this picture?
The line.
Let's start with there.
P prime, wow.
They are not there. They can't be there because they're not given. I don't know.
No, it's that the line is defined by 2 points, not by 3.
Well, and so we've got
And
this
Q
line,
can't be on the same
PQ.
line.
Here's the line PQ, maybe draw that in there. We're trying to draw an impossible picture because we're showing that this is impossible. So there's my impossible picture. What's impossible about that line?
It bends.
It's not, it's
We don't have any notion of bending.
it creates,
It's interior and exterior.
We don't have anything that says that's a problem.
it intersects like
Yeah.
then yeah.
Wonderful!
Yeah.
It intersects L1 twice. It intersects at P prime and Q prime.
Yeah.
Oh.
Can't intersect it.
Remember that, dear?
Where does it say it can't?
Yeah.
That was the, so 2 points define a unique line, right? So P prime and Q prime are 2 points. They define then line L1 and line PQ. So then PQ and L1 are the same line. But PQ and L1 aren't on L1, or P and Q aren't on L1 because they're on the interior.
Yep.
Do you see how that's a contradiction?
Yeah.
Yep.
Should we go over that one more time? Big picture of what we did? Let's restart. And we won't use all the verbiage this time, we'll just talk with the picture. So what's given to us? We're given some angle O. And we're given 2 points on the interior of O. P
Thank you.
and I want to kind of draw them close to this edge so that it's more believable. So that my picture doesn't look too crazy. Here's P, here's Q. So we're given 2 random points on the interior of this angle. What does it mean that they're on the interior of this angle?
That they are on the
They
same
share
side as
one
line
side.
out and line 2.
Yeah, so it means if we extend this and we call this L1, and we extend this and we call this L2, it means that P and Q are on the same side of this line and they're on the same side of this line. Right? To be more clear, they're on the same side of L1 as this ray, R2, and they're on the same side of L2 as this ray, R1. That's the definition of interior, right? So far we're just using interior. Then we said, grab some point A between P and Q, and let's assume by way of contradiction that it's out here. It's not interior, it's exterior. Good?
Yeah.
Now there's 3 ways it could be exterior, right? Well, there's a lot of ways it could be exterior, but let's stick with this for a second. So if A is exterior, then it's either on the opposite side of L1 or it's on the opposite side of L2. Right?
Yeah.
Any point I pick that's exterior, it's either going to be opposite L1 or opposite L2. It has to be one or the other. If it's both, then it's at least one. So it's either opposite L1 or it's opposite L2. We're guaranteed one of those 2 cases. So let's just handle the case that's opposite side L1. To do the proof opposite side L2, it's identical. So let's just handle, it can't be opposite L1. You with me so far?
Yeah.
So let's assume it is opposite L1 and see how that leads to a problem. If A is opposite P on L1, then there has to be some point, and I call it P prime, such that P prime is between those and P prime is on L1, right? And if A is opposite Q, then what do we know?
There's a point
That
between
is
A
Q
and Q.
prime. That
Then there is some point Q prime, such that Q prime is between A and Q, right? And all these points are on the same line, right? Because that is between this and this. That's the first between this axiom. If you have P, A, Q, then P and AQ are 3 distinct points on a line. So we're guaranteed that all these points are on the same line. So there's our line. Now, why is that line impossible?
Because it has more than 2.
Yes, it's intersecting this line at 2 points. Okay? So you get a contradiction. So A can't be opposite side for L1. Similarly, it can't be opposite side L2, so A has to be in there.
And then it's between it, so that.
Well, we already knew it was between it. We were using that information. Right?
Yes.
Everyone understand the proof?
Yes.
This is probably one written in the book. It should be. All the theorems typically are, so you can read how they do it. I don't typically read their proofs when I do my proof, so they probably proved it different than me. And I try not to look at their proofs because I think it's good if you can have 2 different ways to see it. So, good with that?
Yeah.
Theorem 3.5. If R is a ray from O, where angle O exists, and R is not one of its sides, then R is either on the interior or the exterior of angle O. With the exception of the point O. Okay? So this is a real easy one. Let's draw a picture, make sure you understand what it's saying.
Which one is this?
So this is theorem 3.5. So we're given that there is some angle O. There's angle O. And we're given that R is some ray from that vertex different from one of these rays. So maybe we'll call this one R1 and R2. And we'll continue this out. We'll talk about L2. And we'll continue this one out and we'll talk about L1. So now I've got R is coming out from here. And what the theorem is saying is that all the points on R are either interior
Or
exterior, with the exception of the actual point O, because that's on the angle, right? Okay? So first off, if R is exactly on this line, if R is right there, then what do we know?
Exterior.
It has to be exterior by definition, right?
Why?
Because these lines are not on, this ray isn't on this side or this side of the line, right? So it can't be interior, and it's not on this ray or on this ray. So it can't be on it. So it's exterior, because there's only 3 cases. You good?
So it's not on R1, it's not.
So maybe I'll write this out. Observe that if R coincides with L1 or L2, comma, observe that if, okay, I did that. If R coincides with L1 or L2, then it is not on either side of L1 or L2, comma, and so cannot be interior.
Okay, so it's still considered exterior.
And it was given that it wasn't on R1 and R2, so we don't need to specify that case, right? So if it's directly on one of these lines, we know it's exterior, right?
Yeah.
So then it has to be on the sides of the 2 lines, and therefore it's either interior or exterior. I don't need to write that out, right? You can see, that's it, we're done?
Yeah.
All we were proving that was interior or that was exterior. We were proving that it's one of those 2.
Can't be both.
We didn't even prove that some of the points aren't over here and some aren't over here. We didn't even prove that. All we proved is if you take all those points, they're either interior or exterior. They're not on this line, and they're not on these rays. Basically, they're not on this line, they're not on this line. That's what we're saying. Good?
Yeah.
Well, they could be on this line, but if they're on this line, they're exterior. So any points on here, exterior. Any points here, exterior. Any points here, interior. Any points here, exterior. Any points here, exterior. Any points here, exterior. And then they couldn't be right on the rays. So that's a simple proof, nothing tricky here. And now, the final proof that finishes up this section.
Theorem 3-6.
And all the hard homework problems were about this theorem too. So, we'll just do it all in one go. If P and Q are points on the interior and exterior of angle O, respectively, then segment PQ contains a point of angle O. So, let's write that in words. If P and Q are in the interior and exterior of angle O, respectively.
What did respectively mean?
Maintaining order. So in other words, P is the one I named first. So P's in which one I named first? Interior.
Okay.
And Q is the one I named second in the exterior. So respectively means maintaining that order. Respectively, comma. So if P and Q are in the interior and exterior of angle O respectively, then, this is lowercase d, then segment PQ intersects angle O. Okay? Let's get a picture so you can see what we're talking about. So we've got angle O. Once again, I'm going to extend the lines, use our same naming convention. I'm going to call, I don't remember which one I called L1 or 2. L1, L2, R1, R2, that point's O. Angle O is what we're talking about. P is interior, and Q is exterior. Now we've got a lot of cases that we need to handle with Q being exterior. Q could be over here, and I'll call that Q1. That's one possible location. Q could be over here, Q2. It could be right on the line, or it could be somewhere in this part. Or it could be over here, Q3. And then on this line, it's the same as on this line, and over here is the same as over here. So we need to handle these three cases. And show that in all these three cases, then QP intersects that segment.
Oh.
That angle, thank you.
I would say no.
Do you understand the question?
Yeah.
Yes.
All right. So let's begin. All right. So 1. Let angle OPQ R1 R2 L1 and L2 to be as drawn, not including Q. Sorry. Okay, just to save me having to write out a bunch of stuff. Let's say we've got this set up and we're going to go through the different cases of Q. All right? So 2. Let's see which case I start with. If Q is on the same, on this side. If Q is on the same side of L2 as, I'll just write it as I go. So if Q is on the same side of, I might not have done this in this
L1.
case here. Same side of L2 as P.
You could just say if Q1.
Same side of L2 as P.
You could just say if Q1.
But opposite side of L1 drawn Q1. So let's see. Then there exists R on L, which L? L1, such that QP or QRP, right?
Yeah.
So let's go over what we're saying. So we're doing this case first. So I'll draw and erase as we go through case by case so you can see what's happening. So I'm saying, let's say that Q's in this section, demonstrated by Q1. So if it's up here, then there has to be some point on L1, call it R, such that Q1 RP. Now what we don't know is if R is on R1 or if R is down here, right? For all we know, it could go like that. We're trying to prove that it goes through here. Okay? So the way we're going to do it is we're going to show that it's impossible for it to be down here. So 3, assume by way of contradiction that R1 is not, or that R is not on R1. Okay? what do we know if this point's not on R1? If it's down here, what do we know? So let's draw the case we're trying to disprove. Why do we know it's bad for R1 or for R to be down here?
Because then it's not a line.
They'll intersect line 2 twice.
Nope.
They'll
Yep.
only intersect.
Line 2, yeah.
Yeah, perfect. So then between Q1 and R, there's going to be some point here, right?
And then another point.
And between R and P, there's going to be some point here.
Except that it will be on that ray.
Yeah, but it's the same line.
It's still the line.
Well, we don't know that's on that ray necessarily. I mean, for all I know, this point right here,
Yeah.
right?
Well, I'm saying if it was on that ray, it would be
No.
on our ray.
We're drawing an impossible picture. So here's a potential line.
You can't assume it's on the ray because it's on that ray.
Whatever. We don't know that goes through R2. Maybe it comes up in some dimension we don't know about and goes up and over. We don't know.
Oh yeah.
Yeah, maybe. You don't know. But we've got that this line is intersecting at whatever we decide to call that point and whatever we decide to call that point, which is bad. Do you see that? Maybe I won't bother wasting time writing all this out. I'll just show what's bad. So do you see why this case is bad?
Yeah.
Yes.
So it can't be that case. So let's continue to our next case. Q2. So we've got Q2 and P are on opposite sides. And we've got R must be between them. Once again, if R is on R1, we're already done with our proof. Right?
Yeah.
So let's assume it's on R1. Let's pretend it's down here. So we've got Q2 comes down here and then comes up here.
Has 2 points.
We got the same problem.
Line 2.
This point and P are on opposite sides. There has to be some point between them. So Q's on the line and that's on the line. We've got 2 points on the line intersecting. Bad. Right? Let's go to the next case. This is the only interesting case. I'm making a mess of my picture. I'm just going to redraw the picture real quick and then we'll thoroughly go over this one. So R1, R2, L2, L1. So we've got P's here, and we call that point O. And we've got Q's down here, right?
P's and Q's.
Maybe right on the other side so I can draw lines coming out from it. So PQ, if it goes through R1, then we're already done. And we've proven it, right? So let's assume that it doesn't go through R1 and prove that means it goes through R2. So this one's different from the other ones. It's possible for it to not go through R1. All the other proofs we said, let's assume it doesn't go through R1 and we got a contradiction. It had to go through R1. This one, it's possible for it to not go through R1, right? It could actually go like this and intersect down here. So we're not going to be able to say, assume it doesn't go through R1 and get some contradiction, right? So we say if it goes through R1, then it goes through R1 and we're done. If it doesn't go through R1, now let's prove it still works. Do you see the difference between how we're proving it now versus how we did before?
We're proving both of them.
We're saying that, so P and Q are on opposite sides of L1, right? And so there has to be a point between P and Q on L1. It's possible that could be right here in R1, and in which case we're done. And it's also possible that could be down here. In which case we're not done and we still have more work to do. Okay? So first case, easy. Second case, we still have some work to do. Good?
Yeah.
Alright, so let's do our work. So if it's down here, then what? Well, let me do that different. Let's say if it's through R2, then we're done. Now, if it's not through R2, then it has to intersect somewhere over here, right?
Yeah.
So we know that it's this point. Yeah, there's a cricket. You guys aren't responding. I can hear the crickets. So we know this point, R, is on the line. Now how do we continue from there? This is exactly one of the cases that we already proved, when Q was right there. Right? So we've already proved this.
Yeah, you have to have.
How did we prove it? Then R is opposite side of P.
So there has to be a point.
Opposite side of L as P.
Oh, what did we say for that?
That had to go some weird
It
dimension.
has to go through R1.
We don't know.
Can't go through R2. If that's the case.
It has to go through R1. It has to go through R1.
We don't know that
It has to go through R1, but how did we prove that before?
That
for some
we don't
reason
know
this is
that-
not.
Because it
Wait,
intersects L2
contradiction.
twice.
So
It
it,
would have to intersect L2 twice. If it did.
there'd be 2 points.
all right. So it still has. Thank you. So it still has to go through here, right?
Yeah.
And if it goes through here down here, then we have a contradiction.
Yeah.
How do we have a contradiction? Because this point's on the opposite side of that, and so it would have to go through this line again somewhere.
Yes.
Yeah.
Right? So once we got that point on that line, we reduced it to the other proof.
Yeah.
Good?
Yes.
Alright. So all your homework problems are going to be doing proofs for different cases of this.
Upcoming homework? Or just
Yeah, for
what
3-6.
past homework was for?
So 3-6. That's the homework that's going to be assigned. The homework that I'm going to assign you is going to be exercise group 3-6. And then the algebra review at the end of chapter 3. And then maybe some of chapter 4, depending on how far we get. So that finishes off chapter 3. We're done with that theorem. That's the last thing we proved in chapter 3. So now let's go over what we did in chapter 3 real quick to make sure that you remember everything and you're up to date.
Okay.
Good?
Yeah.
So these are all the definitions we made. Make sure they all make sense. We defined the two sides of a line. Not the two sides of a plane, the two sides of a line. We said if you have a line and a point on the line O, then O splits the line into two sides, this side and this side. You remember that definition?
Yeah.
The way we defined it was take some point on the line, draw a line through it, M splits the plane. All those points are on one side of the plane, and all those points are on the other side of the plane. Right? Next thing we defined was a segment. Remember a line segment?
Yes.
Yeah.
Next thing we defined was a triangle.
Which you could clarify.
So line segment, you have 2 points A, B, and all the points in between them. That's a line segment. A triangle is 3 line segments. Well, take 3 non-collinear points, A, B, and C, and then take their line segments and union them together. So all the points on this line segment, or this line segment, or this line segment. Question, is this on the triangle?
Nope.
Are you for real?
Yep.
Okay. Perfect. Where was I looking down? Collinear. What does it mean for 3 points to be collinear?
That they're not on the same line.
They are on the same line. Collinear on the same line. Non-collinear means not on the same line.
Yeah, I don't get
Do we know what array is?
Yes.
Yeah, it's our dad.
It's your dad. Do we know what an angle is?
Wait, about the ray, did you say last time a ray has to be a segment and can't go on forever?
No.
No, ray goes
So-
forever.
A ray is half a line starting at a point. It's all the points on one side of a line, including the point that we start taking the sides from.
Okay.
Now, it goes on forever, meaning that we have our line builder postulate and keep adding points. But we do not yet have a notion of length. We can't say this thing has infinite length, because I can add infinite points in a finite length, right?
Yeah.
What's 1 plus a half plus a fourth plus an eighth plus a 16th plus a 32nd off to infinity? It's 2. That's an infinite number of points contained.
Yeah.
Huh?
That'd be like, I just said that.
All right. So Debbie already knows the answer. Let's continue our definitions. An angle, what was an angle?
It is a set of all the points on two rays.
Two rays with a common vertice. So if we have two rays sharing a common vertice, then that's an angle.
Yeah.
And all the points on those rays.
Yeah, the two rays themselves are the angle. What's a straight angle?
It's where the vertexes share same, where angles share the same
Where the
vertex.
two rays are collinear.
Oh, duh.
Right? What's a vertical angle?
Perpendicular.
Look it, if I draw it up like that, it's vertical, right?
No.
No, what's vertical?
No, we have to have angles that are opposite each other.
Yeah, I have to have two lines intersecting at a point,
They share the same line.
and then this angle and this angle are vertical, and this angle and this angle are vertical,
Yeah.
right? Adjacent angles,
They share one ray and the vertex.
so if I've got this angle like that, and I've got this angle like that, those are adjacent, right?
Definitely not.
No, they have to have a common vertice and a common side. Or in other words, a common ray, right?
Yeah.
Almost. There's one more technicality. Let's say, for example, I was talking about this angle and this angle. Are those two adjacent?
No.
But they have a common vertice.
But they don't have a common.
They are both using this side, common side and a common vertice. Are these adjacent?
No.
No. So the definition states that they have a common they have this adjacent side, and the other sides are on opposite sides of their shared side.
Okay.
Okay? So this picture doesn't work. This picture works.
Yeah.
Good?
Mhm.
What are supplementary angles?
When they
Supplementary
create a
adjacent
straight
angles, I mean.
angle.
It's two adjacent angles that
Create a straight angle.
Two adjacent angles where the opposite side from the adjacent side
Are collinear.
are collinear, sure. They're on the same line. What's the interior of an angle?
They're on the same line as side one, or what? Line one and line two.
Yeah.
Yeah, so take not just the ray, but take the line on that ray, take the line on that ray, take all the points on this side of one line and all the points on this side of the other. That's the interior. And then the exterior are all the points that are interior and that aren't on the angle. Then they're exterior, right?
Yeah.
Does a straight angle have an interior and exterior?
That is a great question. So one of the questions somewhere in here, I don't know where, it says, explain why it doesn't make sense to talk about the interior and exterior of an angle.
Because there's
or
only
of a
one
straight
line
angle.
because they're collinear. There's only one line because they're collinear.
Because there is no
That's why.
interior. A straight angle is
What's your thing?
Because they're both rays are on the same line, then when you take the same side, when you take the line, when you split the sides of, how can I say this right? So when we talk about the interior, we split this into L1 and L2, right? So the interior is all the points on this side of L1 and on this side of L2. Well, when you do that with a straight angle,
Your L1 and L2.
It's the same thing.
then you take all the points on the same side of L1. Well, when we also define that, we call this R1 and R2. So we said, take all the points on the same side of L1 as R1. Take all the points, and we call this one R1, this one R2, and then
And
this
that
one L1 and L2. It doesn't make sense anymore. The definition breaks
Yes,
down.
it does. The interior of a straight angle is the angle.
No, the interior can't be part of the angle.
Why?
That's the definition.
Yeah.
It's all the points on the side of the line, not on the line. Remember that the line splits the plane into three sets. There's all the sets on one side, all the set points on the other side, and all the points on the line. Right? So the points on the line can't be interior because they're not on a side of the line. So it doesn't make, the definition breaks down when we try to define the interior and exterior of a straight line.
Because a straight angle is basically the division of the plane angles.
Well, it's because when I say take all the points on the same side of L1 as R1. R1's not on one of the sides, it's on the line. So the definition breaks down. So we don't have a definition for an interior and exterior of a straight line. Does that make sense?
Yeah.
Great question. And then, oh, did we talk about the interior and exterior of a triangle?
No,
I think
it's
we skipped that, but that's pretty
self-explanatory.
easy.
There's line 3. That's it.
So the interior of a triangle are the points interior to its 3 angles. So I've got some triangle, A, B, C. It has 3 angles, right? Take all the points that are in the interior of angle A and of angle B. Turns out that's enough, but it also says and angle C.
Why isn't it enough to just say one of them?
Because technically these are rays. So the interior of angle C is all this.
Oh, yeah.
The interior of angle A is all this. Now take their intersection, and now you've got the interior of the triangle.
Okay.
Good?
Yep.
Okay. So that was interior and exterior of a triangle. Keep sending down my notebook. No, I wasn't looking at my notebook. I was looking at chapter review. Every time what?
She just lost your
I thought you'd like notice a pattern with the cricket.
Why did you even do that? What's the point of crickets chirping or whatever?
I don't know.
True.
All right. Now here's all the theorems that we proved in this. Make sure you understand them because you're going to want to use them to prove other things as we go from here on out. First theorem we proved in this chapter, 2 different lines intersected at most 1 point. You remember that?
Yeah.
You can now use that for all your proofs from here on out. There are at least 3 lines in the plane.
In a plane.
You remember that?
Yeah.
Good. A point O on a line separates the line into 2 sides.
The 2 sides.
You remember that?
Yeah.
If P and Q are the interior of an angle O, then the segment PQ is in the interior of angle O.
Yeah.
We actually proved that one today. A ray from the vertex of an angle lies, except for the vertex, either in the interior or the exterior of the angle. Remember that?
Yep.
Good. If P is in the interior of angle O and Q is in the exterior of angle O, then PQ intersects the angle. That's the last thing that we did here. Good?
Yes.
So the author actually has a proof for that last one. I would read through it, make sure you understand it. All your homework is going to be based around it. And then the test is just going to be to prove that.
What?
Great.
So now you know what the test is. Come ready to do that. And I'll probably throw some questions from the algebra review in there as well. So.
Okay, so homework is the exercises for 3, 6, and algebra review.
An algebra review. Yes.
Okay.
Good?
Yeah.
Yes.
All right, let's jump into chapter 4.
Do you want our homework?
Oh yeah, I want your homework.
Here, bro.
Okay, chapter 4, we get our next undefined term. What are our undefined terms so far? Point. Line. Plane. Betweenness. Those are our 4 undefined terms so far. And you'll notice those are what our postulates are about. That's what postulates are for. They're to give our undefined terms meaning. So now we're going to come up with our next undefined term, and it's congruent. We do not have a definition for what it means for 2 things to be congruent. We use axioms to give that word properties. Okay? So let's introduce you to the postulates about congruence.
Yay.
I kept these here because I thought we might get to the algebra review, but I decided to continue with chapter 4 first, and then we'll talk about the next algebra review next week after you guys have tried to solve some problems with it. But in your algebra review, everything I had written here, use that for the algebra review at the end of chapter 3. So you can use associativity, commutativity. You can assume you know what plus means. You can assume you know what multiply means. And then you can use those two axioms that we had. Good? Only use those things. Don't use anything else. Okay. So congruence. Congruence is an undefined term. So we have postulates to give us properties of what congruence is. So the first thing is our existence one. So this is postulate 3.1. I won't read the exact verbiage, I'll just show you what it means. If we have points A and B on line 1, on line L I mean, sorry. So here's points A and B. And we have point A prime on line L prime. Let me draw it in the middle. You'll see why in a second. Here's A prime. Then, on a particular side of A prime, there exists one and only one point B prime, such that AB is congruent to A prime B prime. Now, before we continue, the idea that congruence is trying to capture is they're somehow the same. Somehow this line and this line are the same. And the words that we naturally want to put to that is they're the same length. So it's capturing that idea of they're the same length. But we don't have a notion of length yet. We're going to use congruence to define our notion of length. Good? Okay. So we could have also chose B prime over here if we wanted. Okay? So maybe I'll put B double prime so that AB is also congruent to A prime B double prime. Order doesn't matter when I'm writing these. In other words, the segment and these are line segments. So now let's read the exact verbiage and make sure that we've got it right for the picture that we have. Incongruence, the order of the points does not matter. That's not what I'm after. Oh, it's on the other. It's at the bottom of 64. 3.1. The existence postulate for segments. Given points A and B on a line L and a point A prime on L prime, then on each side of A prime, there is exactly one point, call it B prime, such that AB is congruent to A prime B prime. To indicate that AB is congruent to A prime B prime, we write this symbol. So there's a point on one side of A prime, and there's a point on the other side of A prime, such that this is congruent to this, and this is congruent to this. And those are the only ones that we can use involving this point, so that they're congruent to this on this line.
Did it say B prime and B double prime?
No, it said on either side of A prime, there exists a point B prime such that it's true. So we could have put B prime over here, or we could have put it over here. I drew them both up there and drew both up. Hopefully you get it. Okay, number 2.
Are you not going to write it in words?
3.2, thank you. No, you have it right there in front of you, words.
Yeah, but you sum it up very nicely.
So now you sum it up very nicely. Okay, the next one, for those of you that took discrete math, all it says is congruence is an equivalence relation. That's all it says. Let's go over what that means. So, when we say it's an equivalence relation, I'll use that terminology with everyone. We're saying it's an equivalence relation. What we mean is that the relation is reflexive, symmetric, and transitive. So let's go over what each of those means. So we're saying 1, it's reflexive. What does that mean? That means AB is congruent to itself.
Yes.
2, it's symmetric.
Oh. AB is symmetric.
That's what it is.
Good.
That means if AB is congruent to CD, then CD is congruent to AB. Good?
Yep.
Then the third one is called transitivity. It's transitive. And that one means if AB, maybe I'll use primes this time, is congruent to A prime, B prime, and A prime, B prime is congruent to A double prime, B double prime, then AB is congruent to A double prime, B double prime. So for all equivalence relations, these properties are always true. For example, equals is an equivalence relation. So in other words, AB equals AB. And if AB equals CD, then CD equals AB. And if AB equals A prime B prime and A prime B prime equals A double prime B double prime, then that equals. So equivalence relations means that they're somehow the same. That's what we mean by an equivalence relation. So all equivalence relations are reflexive, symmetric, and transitive. An example of not an equivalence relation is less than. Just because A is less than B doesn't mean that B is less than A. Right? In fact, that's not possible. So there's an example of a relation that's not. Let me give you another example of one that is an equivalence relation. Another example of an equivalence relation is has the same parents. I have the same parents as myself. If I have the same parents as Jack, then Jack has the same parents as me. If I have the same parents as Jack, and Jack has the same parents as Jill, then I have the same parents as Jill. Let's look at one that's not like this again. Has one common parent. That one is not an equivalence relation. Do I have one common parent as myself?
Yes.
Yes? If I have a common parent with you, do you have a common parent with me?
Yes.
Yes.
If I have a common parent with you, and you have a common parent with John Doe, do I have a common parent with John Doe?
No.
No? How?
Because just because he has the same parent, it's called divorce.
Right? I could have the same mom as you, and then you could have the same dad as John Doe, and me and John Doe are completely unrelated.
Yeah.
So the brother of your sister isn't necessarily related to you. Right?
Yeah.
Okay. So that's what we mean by an equivalence relation. Congruence is an equivalence relation. Satisfies these three properties. It's reflexive, symmetric, and transitive. And then the last one, for those of you familiar with Euclid's postulates, this one will look familiar. 3-3, it says, if,
Oh, now you're writing it out.
try and keep the verbiage here the same. Okay, so we start out with A, B, and C on one line, and A prime, B prime, and C prime on another line. So if we have, let me draw the picture. I won't bother with words. All right. So if we have A, B, and C on one line, L, where B is between A and C, so assume all the information from the drawing that the line has. And then, if we also have A prime, B prime, and C prime on L prime. So if this is the case, and then if this other information, then conclusion. So if AB is congruent to A prime, B prime, and BC is congruent to A prime, C prime, oops, B prime, C prime, thank you, then AC is congruent to A prime, C prime. This one, they sometimes call like the addition postulate. right? If this segment's the same big as this segment, and this segment's the same big as this segment, then this segment's the same big as this segment, is in a sense what it's saying. So if that's congruent to that, and that's congruent to that, then this is congruent to this.
Yeah.
And you can think about, like, if you add equal things together, the result is equal, is the way that Euclid states it. Kind of. He says it slightly different. But it captures the same idea. And then the other one is the subtraction one. So number 3 split into, I don't know if they do like A and B or 1 and 2, something like that.
A and B.
A and B are, and then if AC is congruent to A prime C prime, and BC is congruent to B prime C prime, then AB is congruent to A prime B prime. And notice this one's telling us how we can take away. So it's saying, look, if this thing's congruent to this thing, and this piece is congruent to this piece, then this piece is congruent to this piece. The way Euclid says that is, if equal pieces are subtracted from equal pieces, the results are equal. Okay? Now it turns out we actually don't need this line here as a postulate. You can prove this from this. We'll most likely do that next week. But for the sake of, you know, it's nice to have an add and a subtract, then there we go. Good?
Yep.
So those are the postulates. There's only 2 theorems that we need to prove in this section, so yeah, maybe I'll give you
There's 3.
the less than and greater than definition. Oh, there's 3.
3 theorems. Yeah.
So I'll give you both the definitions too,
4 actually.
and then we'll call it good and we'll do the theorems next time. So these are all the postulates in this chapter, and then there's only 2 definitions. So the definition, I can't remember if they ever do greater than or less than. So, okay, they do greater than. So they say if we have a picture like this, here's A, here's B, here's A prime, here's B prime.
Both cases, yeah.
So we'll handle both cases real quick. Okay, so let's go over, I'll just read exactly what it says and then we'll talk about the picture. Let AB be any segment and AB prime any other segment on line L prime. So this is on L prime, and then this is on L, I guess.
You said L.
You said L.
I was just testing you. So, on the same side of A prime as B prime,
And B double prime,
Yeah.
right?
let AB and that, okay, on the same side of A prime as B prime, let B double prime be the point such that AB is congruent to A prime B double prime. So we've got some random line segment, some other random line segment. I did these backwards. Here's my B prime, here's B double prime, here's B double prime.
No, I think you did.
My picture's
You got
lying.
it right.
You did it right.
They're using,
B double prime is.
I don't know why they said it that way.
Yeah,
but
you did it right.
the first time. Or you could just do it that way.
I'm just going to do it this way. You'll get the idea and then we'll go over it one more time. So we've got AB here, right?
Right, yeah.
Now on this line, there's only going to be one point on this side of A prime, so that A prime to that point, call it B prime, is congruent to this, right? And there's 3 cases. B prime could be on this, so A prime B double prime is congruent to AB, right? That's what I'm saying. And we're saying B prime could be in 3 possible locations. It could either be to the left of B prime, it could be right on B prime, or it could be to the right of B double prime, or of B prime, right? So either this is congruent to this is congruent to this, or this is congruent to this. You with me?
Okay.
If So if A prime, B double prime, B prime. So if the point that makes A prime, B prime congruent to this is between A prime and B prime, then we say that AB is less than A prime, B prime. If B prime equals, or B double prime equals B prime, then AB is congruent, obviously, to A prime, B prime. The definition doesn't really handle that case, but we'll just put it in there. And then if A prime, B double prime, so if B double prime happened to be on this side of it, then AB is greater than A prime, B prime.
That doesn't make sense.
All right, so let's go over it one more time. So we start out with some segment AB and some segment A prime, B prime, right?
Okay.
Now we draw B double prime on this line so that A prime, B double prime is congruent to this.
But I thought-
So first case, this is congruent to this segment, right?
Size isn't relevant.
Yeah, don't let the picture lie to you. So if this and this are the same
No, but
size.
you just said that A and B prime are congruent to AB.
Okay, let me start out one more time. We're given some segment AB and some other segment on the line A prime, B prime.
Okay.
Okay? Then we draw point B double prime on this line so that A prime, B double prime is congruent to AB.
Okay.
Okay? And we do it on the same side as B prime. So over here. We're not drawing over here, basically. You with me? So right now, this is congruent to this, right? So if that point B prime, that happens to make this length equal to this length, is on this side of B prime, so in other words, we have A prime, B double prime, B prime, then we say that this segment is smaller than this segment. Because it's equal to this segment, right? If that's equal to that, then this is smaller than this. That's what we mean by less than. So if B double prime is between A prime and B prime, so in other words, given here,
Yeah, you have to say it here.
given AB congruent to A prime, B double prime. So we construct B double prime so that this is true. Okay? If it turns out that B double prime is in between A prime and B prime, then AB is less than A prime, B prime. Good?
Mm-hmm.
If it lands right on it,
They're the same size.
so B prime and B double prime coincide, then they're congruent to each other. And then, if it lands over here, so that B prime is in between it,
Then
B prime is between A prime and A double prime, then we say that AB was greater than A prime, B prime. You good?
Yeah.
Maybe I'll draw 3 separate pictures. I think one picture's showing out.
No, you did it. Let me grab it.
First case. Here's AB. I guess we can keep AB there the whole time. So if B prime, so here is A
Get
prime.
the first one, I just don't get the rest.
So let's start with this one. Here's A prime, B prime. Here's AB. If we draw B double prime on this line so that this is equal to this, so now that and that are congruent.
Okay.
If we draw B prime on this line so that that's congruent to that, and we draw on the same side of A prime as this point, so not over here, because we could have also come over here and we could have drawn a point there, so that's the same one to that, right? We're saying don't go that way, only go this way. So if it goes A prime, B double prime, B prime, A prime, B double prime, B prime, then AB is less than A prime, B prime.
Mm-hmm.
Case 1. Case 2. Here's A prime, B prime. We come down and we draw B prime, B double prime, so that this is congruent to this, and it lands on B prime. Then A prime, B prime is congruent to AB.
Okay.
Last case. Here's B prime. We come down and we draw B double prime so that this is congruent to this. If it goes A prime, B double prime, then AB is greater than A prime, B prime.
Okay.
Those are the three cases.
And throughout the whole thing, you're saying that AB is congruent to A prime, B double.
Yeah, I'm always drawing B double prime on this line, so that A prime, B double prime is congruent to AB.
I see.
Okay? And then our last definition is if we want to say that AB is congruent to A prime, B prime, or AB is greater than A prime, B prime, we say AB is greater than or equal to A prime, B prime. So we're just defining greater than or equal to exactly how you'd expect. And similarly with less than or equal to, just switch that, right?
Wouldn't it be and, not or?
Or,
Oh, yeah.
say that, say what that means. How do we read that symbol?
Less than or equal to.
Less than or equal to. Less than or equal to. Good?
Yeah.
Okay, so now you can also get started on chapter 4.